All right, welcome to Unit 11, Lesson 2 on oxidation numbers. So today's learning intention is to be able to assign oxidation numbers to elements and use them to identify oxidation and reduction. Okay, so what does that mean exactly? So if we remember, oxidation is the loss of electrons, right? So when you lose electrons, right, your charge is going to go up because electrons are negative. And reduction is the gain of electrons. So if you're gaining electrons, your charge is going to go down or get reduced, right? So that's reduction. So that's you can look for that if charges are indicated, right? So if you have an ionic equation where you have ions turning into atoms, or vice versa, um, it's fairly easy to tell what's being oxidized and what's being reduced. Now, if you have I guess, a regular chemical equation, right, that doesn't involve ions, um, now the charges of each specific element aren't going to be indicated, so it's a lot harder to tell what's being oxidized and what's being reduced. So to do that, we have to assign each element in a chemical equation an oxidation number, and then we look at the oxidation numbers and see if they change, right? And if they go up, that means oxidation occurred at that element. And if an element's oxidation numbers goes down or gets reduced, it's reduction. Okay, so the first step in this is being able to assign elements oxidation numbers, and there's quite a bit of rules that go into assigning these oxidation numbers. All right, so before we jump into that, let's make sure we can determine oxidation and reduction for ionic equations where the charges are already given to us. All right, so go ahead and pause the video and try out this multiple choice question here. Okay, hopefully you paused and tried that. So what do we got here? We have zinc solid, right? No charge, so that's just an atom. Combining with or reacting with a copper ion, 2 plus charge. And then afterwards we have zinc with the 2 plus charge and copper that is has no charge. Okay, so it's asking which equation represents the oxidation half reaction. So pause. Okay, oxidation, right? If you remember, Leo says GER, so LEO, loss of electrons, oxidize. Okay, so oxidation is the loss of electrons. So we're looking for which element, okay, because it's a half reaction, it's just all about one of the elements, right? As you can see, they're all just about one of the elements. Which element is losing electrons? Well, if we look at our equation, right, if you're going to lose electrons, that means your charge is going to go up, okay? So if we look at zinc, zinc starts off with a 0 charge and ends up with 2 plus. That's going up, all right? And copper goes from 2 plus down to 0. That's going down. So it looks like zinc is the one being oxidized because the charge goes up, okay? Now, which equation represents that, right? So it's either going to be A or B because we're talking about zinc and not copper. And we want it, right, if electrons are being lost, that means the electrons are going to be on the product side, right? So here we have, right, we have zinc on the reactant side, and the arrows are kind of weird here. I don't know why they're like up like that. And then on the zinc on the reactant side, solid, and then on the product side, we have a zinc ion and 2 electrons separate. Now, an easy way to not choose A by mistake, right, is look at the charges on each side of the arrow. They have to be equal. So in A, the total charge on the left here is, this is 0, but the electron is 2 minus. And the total charge on the right is 2 plus. Now that's not balanced, right? Charge also has to be balanced in equations. So that's an easy way to get rid of A, right? If we notice, here's the arrow. So on the left side, on the reactant side, the total charge of everything over here is, this is 0, this is 2 minus, 2 electrons. And then on the right side, it's 2 plus. That's not balanced. In B, we have the total charge on the left side of the arrow, so here's the arrow, is 0. It's just zinc over here with no charge. And on the right side, we have a 2 plus and a 2 minus for a total of 0. Okay? So that's an easy way to eliminate A because it doesn't follow the law of conservation of charge. All right. And another way to think about it is oxidation is the loss of electrons. If you're losing electrons, then it's going to be separated on the product side, right? You can think of it like before and after. Before, the electrons are part of the zinc atom, and then after, they're separated, and that's showing that it lost those 2 electrons. Okay, so zinc here was oxidized, and it's represented by B, and the copper was reduced. Remember, reduction and oxidation always occur together because those 2 electrons that were lost by the zinc were gained by the copper, right? And that's represented by equation D. This is the reduction half of the equation, right? Okay. Oh, yep, there's my cat making noise during my video. All right, so this was relatively easy because it gave us the charges, right? Now, it's not always going to do that. So in an equation where it doesn't give us the charges because there's no ions involved, there could be ionic compounds, but they're not free-floating ions, so the charges won't be indicated. We have to know how to give what's called oxidation numbers. Okay, so we can keep track of the apparent charge, right? It's all about keeping track of the apparent charge of an atom, right? Oxidation numbers are made up. They're just a system for us to keep track of what's being oxidized and what's being reduced. Okay, so there's a bunch of rules for assigning oxidation numbers. So this is something you definitely want to look into and review maybe a couple times. I also have a nice flow chart coming up that makes the rules look a little bit simpler. So let's dive into these. So first of all, free elements. So elements all by themselves, okay, are always 0. They always have an oxidation state of 0. So if it's iron by itself, if it's silver by itself, and don't be fooled, this is the same element. It's just a diatomic molecule of bromine. Okay, these are all what we call free elements. They're all individual. They're all by themselves. They're not combined with any other element, and they always get an oxidation state of 0, oxidation number of 0. Okay, the group 1 metals. Okay, remember, group 1. You should always have this handy, right? Group 1 is here. Okay, so group 1 metals. So you ignore hydrogen. We got lithium, sodium, potassium, rubidium, cesium, francium. Okay, the group 1 metals always have an assigned oxidation state of +1. Okay, positive 1. Now notice oxidation states, the charge or the sign, the plus or minus comes before the number, and in a charge, the plus or minus comes after the number, right? That's how you can distinguish the two. So group 1 metals, always a +1 charge, or a +1 oxidation state. Group 2 metals, okay, that's here, group 2, always a +2 oxidation state. All right, so that's easy to remember. Group 1 is +1, group 2 is +2. Also, zinc and cadmium, I believe that is, are always assigned a +2. So zinc is here, these guys over here. Right, you can see it, right? On the periodic table, it gives you the oxidation numbers. That's what those numbers are in the top right-hand corner. Okay, so zinc is just 2 plus. Cadmium, I believe that's cadmium, number 48. Let me check. 48. Yeah, cadmium. Okay, cool. Yeah, those always have a 2 plus as well. But you'll notice all these transition metals, or most of them, right, can have many charges. I mean, look at manganese, +2, +3, +4, +7. Could be lots of stuff, right? That's where it's going to get a little tricky. Okay, so group 1 metals, +1, group 2 metals, +2. Fluorine, specifically, always gets a -1. It's the most electronegative element. It's always a -1. Hydrogen is always a +1. Okay. So you could group that into kind of the group 1 metals, even though, remember, hydrogen is not technically a metal. It is a non-metal. Okay. Oxygen is always -2. All right. Right. It usually has a 2 minus charge as well, so it's kind of easy to remember it that way. And this is where it gets a little tricky, right? Because now we have to think about, okay, what about all the other elements? Well, they can be different. They can have different oxidation states, right? So here are the definites. Free elements 0, group 1 +1, group 2 +2, fluorine is -1, hydrogen's +1, oxygen's -2. Now, here's maybe the tricky part. Okay, so the sum of the oxidation states of all the atoms in a species, so it could be a molecule, compound, must be equal to the net charge on the species. All right, so let's do an example of that, because that's like, what does that mean? So here we have SO4 2 minus, right? A sulfate ion, polyatomic ion. Now, we didn't say anything about sulfur, right? So how do we know what the oxidation state of sulfur is? Well, what rule 7 tells us is that when I add up the oxidation states of 1 sulfur and 4 oxygens, it must equal the charge of 2 minus, okay? And sometimes there won't be a charge there. That just means the charge is 0, and it will all add up to 0. But in this case, the oxidation numbers of sulfur and 4 oxygens will all add up to 2 minus, okay? So since each oxygen is negative 2, minus 2, and the oxidation numbers add up to negative 2, right? We can do a little math here. Sulfur plus the 4 oxygens, each at negative 2, have to be equal to negative 2, right? Okay, so sulfur must be, the only way this works, right? Do a little quick algebra. 4 times negative 2 is negative 8. Bring it over here. By adding it, makes this positive 6. So sulfur in this compound, not all the time, has an oxidation state of plus 6. Okay, and you do that by coming up with the oxidation states of what you know and then using it to fill in what you don't know. Okay, and we're going to practice this in this lesson multiple times. All right, so there's rules for a good amount of the elements, and then when there isn't a rule, you have to do a little bit of math. You have to do this out. Okay. All right, so here's a nice little flow chart I made that you can start to help you as you are assigning oxidation numbers. Right, it's basically what I just went through. Right, if you notice these are all the rules, and then this is what that last part. So is the element by itself? Then yes, it's a 0. No. Group 1 metal? Yes, it's plus 1. No. Is it a group 2 metal? Then it's a plus 2. But if not, is it fluorine, which would make it a minus 1? No. Is it hydrogen, which is a plus 1? No. Oxygen, which is a negative 2? No. And if it's not any of these, then you have to do a little bit of math, where you add up the oxidation numbers of the other elements in the compound, and that plus your unknown oxidation number will equal the charge on the compound, and you need to do a little, very simple algebra there. All right, so let's do some examples. Get my pen out here. Okay, so CaCl2. So I'm looking at this, right? Now I know calcium, I'm pretty sure, is a group 2 metal. Let me check. Calcium, Ca, yep, that's a group 2. So that means it has to be right, group 2 is positive 2. So calcium, I'll write it right above there, has to be positive 2. Okay. Chlorine, well, let's do this. Let's think about this, right? There's no charge on this, which means CaCl2, all the oxidation numbers should add up to 0 because there's no charge up here. So there's 2 chlorines, and I need to balance out a plus 2 charge. That tells me that each chlorine has to be minus 1. Because if we have 2 calciums, we have 1 calcium at 2 plus, and 2 chlorines, the 2 chlorines have to add up to 2 minus, and there's 2 of them, so each one has to be minus 1. Okay? All right, next example, silver. This one's quick. Why? Because it's an element all by itself. Element all by itself is always an oxidation state of 0. Done, every time, okay? And when we say all by itself, we mean it's not in a compound like all these other ones, okay? All right, we have iron oxide here. So oxygen, I know there's a rule for oxygen. Let's see, what was it? Is it oxygen? Yes. Oh, minus 2. So I'm going to give oxygen that minus 2. All right, and now that I have that, I can use it to figure out what iron is. Okay, so oxygen's minus 2, and there are 3 of them for a total of negative 6, right? That's all the oxygens combined, right? Negative 2 times 3 is negative 6. So whatever iron is, notice the charge is 0. Whatever iron is has to add up to 0, okay? Has to equal 0. Now, look at, there's 2 irons, right? So there's 2 irons. This is tough. 2 irons. Okay? So 2 irons minus 6 has to equal 0. So each iron, right, you could do a little quick math here, is going to have to be plus 3. Okay? Right? It's all about adding up to that charge. And notice none of these have charges, which means they're all neutral, which means the charge is 0. So they're adding up to 0. All right, let's try this last one here. Ag2SO4. Oh, we have 3 elements in here. Okay, well, remember, I have a rule for oxygen, right? So let's get that rule in there. -2. Okay. Now, silver. So we don't have rules for silver or sulfur, but there is one thing I didn't include in this chart here. And you can, if you're, when in doubt, periodic table. And Ag is actually one of the elements. There's a few elements in here. I didn't list all of them that only have one oxidation state. And if you find Ag is one of those. It can only be a +1. All right. So zinc, cadmium, silver. There's a few others in here. Right. You can always just look here on the periodic table. However, if you get to one that has multiple charges, then you have to do the math. But in this case, silver, and I wanted to point this out because it's the rules aren't all-encompassing. This is all-encompassing, right? So silver can only be +1. All right. But sulfur, I'm going to have to look. I'm going to have to look what sulfur is. Or not look, but do the math. So I have Ag, I have 2 silvers, each is +1 for a total of +2. Okay, from silver. Oxygen, there's 4 oxygens at 2 minus each, that's -8. And all of these, including sulfur, has to add up to 0, right? So we have, if I do this, right, whatever the sulfur is, plus, right, -8 plus 2, or I guess -6, right? Is there an eraser on here? Yes, nice. Right, so sulfur -6 is going to equal 0. That one's pretty easy, right? And again, that's sulfur, not a 5. Sulfur has got to be +6, right? Okay. So that's terrible, +6, but hopefully you can hear me. All right, so that's how we assign oxidation numbers when we aren't just given the charge. Okay, now we're going to use that in the next piece here. All right, so we're going to use oxidation numbers to determine which element is oxidized and which is reduced in a chemical equation. Okay, so the first step is to assign oxidation numbers. So let's do number 1 here. Which element is reduced and which is oxidized in the equation below? All right, so we got to assign oxidation numbers to everything on the reactant and product side. So first we're going to start with aluminum all by itself. That's a 0, easy. Then we get oxygen. Careful, it's not -2 because here oxygen is all by itself. Any element by itself is 0. Okay, so those are both 0 because they're both free elements, as we say. Now over here in the compound Al2O3, yeah, oxygen is a -2. Okay, so oh, there's my cat again. Hey, chill, I'm doing a lesson. Okay, so oxygen's -2, and there are 3 of them for a total of -6, right? And there's 2 aluminums, and when we, the 2 aluminums -6 has to equal what? Well, the charge, which is 0. So it has to equal 0. Okay, so what times 2 is going to give us 6? To cancel this out, that would be 3. All right, so we signed our oxidation numbers. Now we got to look. Okay, so let's start with reduction. This is easy, right? Because reduction, you're literally looking for which element does the charge go down or the oxidation number go down, which element is reduced. So if we look, oxygen goes from 0 to -2. So oxygen gets reduced. And then aluminum goes from 0 to positive 3, which means it's losing electrons and being oxidized. So aluminum is oxidized. Okay? So in this reaction, right, we can tell that aluminum is oxidized because it's losing electrons and it's going from a oxidation state of 0 to plus 3. The oxidation state goes up. Reduction, the oxidation state gets reduced. And in this case, it's oxygen going from 0 to negative 2. Let's do one more example here. Which element is reduced and which is oxidized in the equation below? All right, so first we got to assign our oxidation numbers. Okay, okay, this is kind of a tricky one. AgCl. We remember that Ag is one of those ones that only has one oxidation state of +1. And if you don't remember that, look at your periodic table. So definitely when you're doing these, have your periodic table out. And you'll be looking in the top right-hand corner for the oxidation states. And if there's only one number up there, okay, then use that number. But if there's multiple numbers, don't guess. You have to do a little math. So, but for Ag, we know it's +1, +1. For chlorine, right? Well, +1. How do I balance that out to get to 0? That one's pretty obvious. -1. Okay, right? Because there's no charge. Okay, so chlorine has to be -1. Well, let me look at chlorine. Yeah, chlorine can have a whole bunch of different oxidation states, right? So you do have to do the math every time because it could be -1, +1, +5, +7, right? Okay, so those are good. Copper, all by itself, it's got to be 0. Don't even have to look. And I'm just going to do this one real quick because I'm noticing this is all by itself, so that's a 0. Okay. Now we got a compound, so we got to look into it. All right, we got copper chloride. Oof, I don't have a rule for either of these. Let's see if copper only has one oxidation state. Nope, it could be +1 or +2. That's going to make this a little bit tricky here. So if we think about this one's actually kind of difficult. So chlorine here is actually, I'm going to tell you, is going to be -1 because this is an ionic compound, and in an ionic compound, they usually have the same oxidation state as their charge. Okay, so chlorine here is going to be -1, and copper, right? Copper is going to be the same as its charge. So you can think about it. You can do the reverse crossover method to figure that out. Okay, but copper here is going to be +2. Okay, and that only works for an ionic compound, right? You can give it just the charge. The oxidation state is the same as the charge of the ions. So that's actually that could be an extra rule there. Okay, right? That worked out here as well. Silver has a 1+ charge, +1 oxidation state. Chlorine has a -1 charge, -1 oxidation state. So the only time chlorine is not going to be -1 is if it's in a covalent compound, right? So for ionic compounds, you can use the charge, right, which is given by which group it's in on the periodic table. All right, so we got the oxidation numbers. Which element is reduced and which is oxidized. So if I'm looking here, silver goes from +1 down to 0, right? So +1 reduced to 0, that's the one that's reduced. So silver, Ag, is reduced. Okay, now notice chlorine doesn't change. So chlorine doesn't get oxidized or reduced in this equation. Okay, so that means what gets oxidized? Well, it's probably copper. Let's make sure. Copper goes from 0 to +2. That means the oxidation number goes up. That means it lost electrons. Losing electrons is oxidized. So here the copper is oxidized. Okay. All right. So definitely look over that again, right? There's a lot going on here. And when you're ready, go on to the check for understanding. Okay, so you're assigning oxidation numbers here. You're doing what we just did with the equation, determining what's reduced and what's oxidized, and then I have a little challenge question for you. Okay, so go ahead, pause, and then restart. Okay, so number 1. Assign oxidation numbers to each element in the compounds below. All right, so oxygen, right? Hopefully you noticed that was all by itself, therefore it's a 0. H2O, right? Oxygen, when it's in a compound, is -2, and hydrogen is always +1. There are rules for both of those, right? And it works out because the -2, and there's 2 hydrogens each at +1 for a total of +2, balances out the -2 of the oxygen because there's no charge up here, so they should equal 0. Now we got silver nitrate. Okay, so let's start with oxygen. We know that's -2. By now we've seen silver so much, we probably know it's +1, but you can look in the periodic table for that. Okay, so now we got to figure out what nitrogen is. So if silver's +1, so we got a +1, and then we got nitrogen, and then we have 3 times negative. Remember, there's 3 oxygens each at -2 for a total of -6. Okay, so -6 plus 1 is -5, right? And then that means nitrogen has to balance that out. Always look for the charge, right? Most of these aren't going to have charges, but sometimes they might. So whatever nitrogen is, -5 has to equal 0. So that means nitrogen is +5. Okay. And that was it for number 1. Number 2, which element is reduced and which is oxidized in the equation below. So first we got to assign our oxidation numbers. Copper, all by itself, is 0. Yep, I'm seeing another one all by itself. I'm going to give that a 0. Now some tricky ones here. Okay. Now you can ignore the coefficients. They're not going to change the oxidation states, so you can ignore that too. All right, so we have AgNO3, Ag when it's in a compound, right? We remember silver, we probably got this down by now, +1 oxidation state. Oh, we just did this one. Look, I'm just going to steal it from here. Probably did that on purpose. -2, so that means nitrogen's +5. Okay, over here, okay, oxygen, we have -2. All right, and here's one of those examples where, okay, copper and nitrogen both don't have set oxidation numbers, right? Nitrogen can be, oof, look at all those. Nitrogen can have a lot, and copper can have +1 or +2. So how do we know which, if copper is +1, +2? Look at the ionic compound. This one's pretty tricky, actually, okay? So NO3 is a polyatomic ion. And if we look at our table of polyatomic ions, which is somewhere in here, there it is. NO3 has a minus charge, has a negative, a 1 minus charge. Okay, so and there's 2 of them for a total. This whole thing is 2 minus. So that means to balance it out, copper has to be 2 plus, which means its oxidation state is +2. All right, so that was pretty difficult. Okay. So when you're stuck like that, when you have 2 elements left and they both could have multiple oxidation states, you have to notice that it's an ionic compound and then figure out what the charge of the ion is. Okay. All right. So now we have a total of how many oxygens? We have 3. Times 2 is -6. Okay, which means -6. Let's see here. And we got a 2 plus from copper. Yeah. Oh, another easier way to do this too. I want to mention, since we know NO3, right? NO3 polyatomic ion has a -1 charge. We know that the nitrogen and the oxygens, when you add up their oxidation states, they have to add up to -1. So we can actually even ignore the copper here and just focus right here because when you have polyatomic ions, right, it's going to be the same as this NO3. It's actually not going to change. So this is also +5. Okay. So that's a trick you can do for polyatomic ions. You can do them separately. Okay, NO3 is its own unit, right? So that might even be an easier way than figuring out what copper is first. Okay, I was just kind of realizing that, if you noticed, as I was going there. So when you see a polyatomic ion, go to your table, figure out what the charge is, and in nitrate, right, nitrate, the nitrogen is always going to be +5 because the three oxygens are -6, and -6 plus 5 brings you the charge of -1. Okay. Okay, so then we want to know what's reduced and what's oxidized. So copper, I'm seeing, goes from 0 to +2, meaning it's losing electrons. The loss of electrons is oxidation, so that's copper. And I'm seeing that silver, right? Notice that oxygen and nitrogen, they don't even change. +5, +5, -2, -2. Silver goes from 1 plus down to 0. It gets reduced down to 0. So in this case, silver is getting reduced. Okay. All right. So for the challenge question here, I'm actually running out of time. I got 3 minutes before our meeting here. If you want me to go over the challenge questions, try them out. They're interesting. I'll give you a hint, right? Each one of those is going to give you a problem. There's going to be all of these break the rules, and you can see if you can figure out which rules they break. And if you want me to, want me to go over these, come on into office hours or shoot me an email. I'm just running a little on time here. I want to end this video. Okay. So this is a tricky lesson, right? I know it is. There's lots of numbers, lots of stuff everywhere. Feel free to rewatch. You can come in, right? The homework's not going to be due until Tuesday, so come into office hours today, which for you would be Friday, Monday, and we can go through it. Okay. See you guys later.